No, is it right? Or yes? Did I do my whole form definition class lecturing? Let me see. Whole form definition 2. Was done. No, not yet. Okay. Then, according to the schedule, I should start my lecture on whole form definition part 2. And then we can go on to Gihan-Kim's discussion session. And then this one is missing because Jihab had dropped out, so I may fill up this part for first part of lines. So then we may have a next Tuesday. We can start with the discussion led by Adib, and go on to my second part of lines actually. Okay, so let me start second part of a whole form definition class, and go on to discussion session. And during the break time, we can discuss further on maker class hours. All right. Any question? No. Then we can move on to the second part of whole form. So this is the book, this is the chapter, and this is the part I'm trying to cover, whole form definitions. Continuing on the lecture by Barakat, Tuesday. So there are several coefficients to represent whole form shape. And most important one is CB. CB we call the block coefficient. Block is a box, right? So how full of box, the shape of the ship is similar to a block. So it's saying blockiness or fullness of the underwater hull. So this coefficient is mostly focused on underwater shape, not including above water shapes, because that is important for speed and weight and buoyancy things. CB, so for typical number of CB, one means rectangular box. There are such a ship. We call that is a pontoon, or there is another name called barge, B-A-R-G, barge. So let me write down this. Barge is another similar one. That looks like not exactly number one, but almost. Let me show you here. Barge. Barge has very high number of CB numbers, and that 0.9 is still high. And for Great Lake bulk carriers, you see in last time lecturing, self-unloader, which has a conveyor belt at the bottom of the cargo ship, so that there is a boom, so we can unload bulk cargos automatically. Because of that, and the Great Lakes bulk carrier has a special shape because they should pass through channels and locks, similar to Panama Canal. And that is because that channels and locks are very narrow between big lakes, and also they travel along the river, not only Great Lakes. So their shape is very special, long and box shaped. That's why they have a high number of block coefficient. And barge is a box shaped ship. And 0.5 is low, you can say low range of block coefficient. And oceanographic research vessel, it has that kind of range of coefficient. And the definition, this is a LBT, is a length, breadth, and depth. Because we are only talking about underwater body, there is a size of the box that can contain the ship, underwater body. Right? And then volume, VOL is the volume of the ship. That is also the volume of the underwater. So that is a definition of block coefficient. So high CV, same as 1.0 or 0.9. That usually gives you box-shaped ship so that it is a low speed. But because the volume is higher, so you can carry more cargo than low CV. So low CV, that is good for speed. This is thin and slender. Right? You imagine Barakat explains about the Japan Navy ship when in 16th century, there is a war between Korea and Japan. Comparing to Korean battleship, that is very full. So block coefficient is high for the turtle ship. And seakeeping is good for low CV. Seakeeping is how well behaving along the seaway. We call it the seakeeping. So in more technical way, we can say the motion of the ship in a rough sea, high waves, high wind, the ship must be disturbed. Right? The motion is higher, pitching, rolling, and heaving. But for the low CV ships, seakeeping quality is good, better than the ship with high CV. So this is a picture of block coefficient. So that LBT is length, breadth, and depth. So we see only the underwater body. Above water body is not shown here. So underwater hull form. And definition is volume of surrounding rectangular solid, and then volume of water displaced. So same definition as previous. And in terms of showing the above water hull shape is together, it looks like this. The real situation. But still, the block coefficient definition is same. And then mid-section coefficient. This is the maximum section coefficient. But there is another writing there, should be writing. So this is CM. So CM is the symbol for midship. Midship means the center of the ship along the length dimension. At the center of the ship, you can calculate coefficient by dividing the area with a box or rectangle of breadth and depth. But there is a similar one, but a little different coefficient called the maximum section coefficient. and that is a maximum area section. You think about a fish. Usually the mid section, along the middle length section can be the maximum, but sometimes they are not. Or say, if you think about your body, where is the maximum area when you have a sectional area cut in? Probably around the hip, or probably around the chest, or some people with a fat belly, then it can be near the center. Depending on the situation, the maximum section coefficient, the location and number can be different. But anyway, midsection is at the center, and AX is underwater area is greatest. Another coefficient called the prismatic coefficient is called the longitudinal prismatic coefficient, so that there is length and maximum area, and then volume is divided. Right hand side here, you see a mark which is representing the symbol for midsection. So this is a typical mark is shown on the drawing, and that is also symbol of the Society of Naval Architecture in the United States. They adopted the midsection symbol as the society symbol. So this is the definition for CP, prismatic coefficient, and the AX, this is the AX, maximum transverse underwater area. Usually the big ship has usually central midship section is the maximum, but small ships may have not the maximum at the middle of the length. And underwater hull form, so that the CP is defined by volume divided by another volume. That is this box with a CX as the sectional shape. Question? Simple?
Professor, I had a question.
Sure.
So CM is basically the cross-section area of the midsection as shown here, divided by the
Divided by a.
Can you hear me?
Yes, go ahead.
Okay, so I was saying that the midsection coefficient is basically the cross-section area around the midsection of the ship divided by the breadth and width of the prism, right?
Right, B and T is the same.
So B and T is like a rectangular box that was drawn.
Right.
And so in that case, what is the prismatic coefficient?
Oh, prismatic coefficient is different one. So the midsection coefficient is based on area, right? But prismatic coefficient is based on volume, not area.
You see, and the maximum section could be either the midsection or it could be any other section, right?
So say again, maximum area section is near midship. But
it depends on the ship.
Near the center of the ship. But at the front and back end, the area is very small, right?
Yeah,
So this this picture shows that prismatic coefficient. How slender at the front and back is showed by CP numbers. Right? If the ship is very blocky and full, then the CP also similar to number 1.0. But this ship shows that front part is very narrow at the front here, right? Front is very sharp, so that the division by L multiplied by AX, that is this area, AX, this is the AX, and length is L. So this box is the dividend below, the volume of surrounding prism. And the real ship is above, the volume of the ship underwater. So the CP number shows us how slender at the front and back side. Did you get it? But this one is different.
Yes.
This is based on area, not volume. And many ships, the big ships, CM and CX is the same. But small ships, sometimes they are different. Okay. When you see a sailing yacht, the maximum area is a little bit behind the center of the length. And small ships usually do that. Very similar to fishes. All right, let me go on to any other question then? No, so we can move on to this one is water plane coefficient. So this is also area based, not volume based. So the area, this is area of the water plane. Okay. Water plane is water, it's a draft line. Cut in draft level. Then we can see the checked area, that is becomes a water plane area, and rectangle by multiplying L and B. So L and B divided by this shows a water plane area coefficient. So full ships, box shaped ships probably have a higher value of CWP. So it also shows how thin or how slender is the ship, or sharp in the front. And then we can use that coefficient for the real design afterward. So there is another number, well known, crude number. And speed and power characteristic is determined by Froude number. And this is a non-dimensional speed size ratio. In old days, before Froude create this number, find this number, Froude is a personal name, right? In early 19th century or late 19th century. I'm not sure, or 20th century early. But anyway, before Froude create this number, ship design is already done for 1,000 years. So they use different numbers. And at the bottom part of the slides, they are saying speed length ratio. That is similar but different. The speed is divided by square root of length, only length. There is no gravitational G coefficient. And also the unit is different. In old days, they use knot here, and also they use feet here in length. But for the non-dimensional coefficient, you need to have a same unit, say metric unit, or so that if you g can be acceleration, so you need to use the same baseline of unit. So usually we use a metric unit and speed and time section instead of knot and feet. Anyway, but they used in old days, so that you can imagine that they are similar, root number and speed acceleration. 5 feet naval vessel moving at 35 knots. 35 knots is very high. Because this is a Navy vessel, they requires high speed with a big engine. And it can be calculated as a fruit number 0.45. And if the same ship at 10 knots, the fruit number can be very small, right? Because of the equation, the definition is here. But smaller ship with a 150 feet research vessel at 10 knots, fruit number is doubling, almost doubling of 10 knots of big ships, right? Because of this equation. But this is a non-dimensional equation, so that you can, as a designer, you can imagine that big ship is easy to have a higher speed comparing to the small ships. That is the nature and physics behind. So that is another advantage to build a big ship rather than small ship. All right, question?